So in the first half of this lesson, we're going to introduce what it means to graph a rational function. What we did in the previous section, we called those reciprocal functions. They're still in the category of rational functions. They're just a simpler version. They're like a more elementary version of the rational functions, just to kind of get us started so we know, the basics of graphing a rational function. So now we're moving into any old rational function. So let me show you the definition. It changes a little bit from what the reciprocal function is. The rational function is an equation of the form this. It's got f of x equals a of x over b of x. All right, so the difference, the reciprocal function had a constant up here and a linear function down here. Here, a of x and b of x are any old polynomial function. All right, so where a of x and b of x are polynomial functions, so they don't just have to be linear, they can be any polynomial functions. And b of x, the denominator, cannot equal 0. Okay, because we know that. We've seen that rule plenty of times by now. If the denominator is 0, it's undefined. Undefined is bad. So we've got three different pieces that we're really going to look at to graph these rational functions. First is the 0. We've used the word 0. We've used root. We've used x-intercepts. This chapter in the book, they use 0, so I'm going to use 0. A 0 of a rational function. So here's our format right here. This overall thing is going to be equal to 0 whenever a of x is equal to 0. Okay, so 0 of a rational function occurs at every value of x for which a of x equals 0. Okay, so if you want to know where the zeros of the function are, set the numerator equal to 0. You'll find the zeros of the rational function. Okay, vertical asymptotes, we did this in the last section. If the denominator is 0, that's a vertical asymptote. Okay, vertical asymptotes occur whenever b of x is equal to 0. And then horizontal asymptotes. We've got a couple of weird rules here. All right, we've got 3 rules, and you're only going to have one horizontal asymptote. You might not have any at all. All right, so let's start. The first rule, I'm going to do kind of some shorthand here. Let's say if the degree of the numerator is less than the degree of the denominator. Okay, so the degree, remember, is the largest power. So if you have like an x squared plus 2, the degree is 2 because of the x squared, that second power. So if you have a smaller degree in the numerator than you do in the denominator, your horizontal asymptote is just going to be 0. Okay? And that's the function that we saw in the last lesson. All right, so I just want to put something on the screen really quickly just to remind you of that, looking at that parent function. So here we saw this parent function had an asymptote of y equals 0, and that's because this is technically a degree of 0, this is a degree of 1, this is a smaller degree, and so 0 is my horizontal asymptote. All right, but we're no longer looking at just functions like that. Now a of x could be anything, b of x could be anything, so we have 2 other rules. There's one to say the degree of the numerator is bigger. Okay, so say for instance the degree of the numerator is bigger. What ends up happening here is that there actually isn't a horizontal asymptote. Because if the degree of the numerator is larger, it's just going to keep growing and growing and growing and growing. It's not going to approach anything. Okay, so there is no horizontal asymptote if this is the case. All right, and then we have this last really weird example. Let's say the degree of the numerator is equal. That's our third option to the degree of the denominator. What ends up happening here is the horizontal asymptote is this little ratio. We've got y equals the leading coefficient of a of x divided by the leading coefficient of b of x. I'll give you guys a second to write this down. Okay, so that one's a weird one, but we've got 3 different rules for horizontal asymptotes. The best thing you can do is just kind of memorize them, but there are 3 pictures down below that should hopefully make them make sense. So this first one, when the degree of the numerator is smaller, that matches with this picture right here. If you look at the function in the box, 3 is the numerator. That has a degree of 0 technically because there's no variables at all, so it has a 0 degree. Here, x squared is a degree of 2. So the numerator's degree is smaller. It falls into this category. The horizontal asymptote is 0. So you can see right here at y equals 0, there's a horizontal asymptote because this graph is getting really, really close to it, but not actually crossing or touching. This, where the degree of the numerator is larger, matches with this function right here. The x squared is a larger degree than the x, and so there is no horizontal asymptote. You can see these arrows just keep going down and down. These arrows just keep going up and up. There's nothing that it's approaching. And then this last one, the weird example, if the degrees are equal, that matches with this one right here. 2x has the same degree as x. The horizontal asymptote is the ratio of leading coefficients. That one's weird. It'll take a second for us to wrap our head around it. But this leading coefficient is 2. This leading coefficient is 1. So the horizontal asymptote is 2 over 1. And so you can see this is the line y equals 2. So that is the ratio of the leading coefficients. So, like I said, might take us a while to get used to that one. I think that third one is the weirdest rule. So a quick note, and sorry, this line got kind of messed up with my pictures here, but zeros versus vertical asymptotes, a very, very important thing to keep in mind. If you're trying to find the zeros, you set the numerator equal to 0. So the numerator, remember, we represented it as a of x. And then if you want to find the vertical asymptotes, you set the denominator equal to 0, because that would be where your expression is undefined. If you set the numerator equal to 0, that's where it's equal to 0. If you set the denominator equal to 0, that's where it's undefined. So zeros versus vertical asymptotes. Sorry that this graph kind of snuck in here. And then for all of these, vertical asymptotes are where the denominator is equal to 0. So here, the denominator is equal to 0 at -1. That's this line right here. Here, x squared minus 1 is equal to 0 at either plus or minus 1. So you actually have 2 vertical asymptotes in this one. And then here, x minus 3 is equal to 0 when x equals 3. So there's our vertical asymptote over here. Okay, so kind of an introduction there to what it means to have a vertical asymptote, a horizontal asymptote for functions that are more complicated than the ones that we were looking at in the last lesson. So I'm going to start you guys off with a step-by-step. The only ones that we're going to be doing today are these ones. These ones where the degree of the numerator is larger. So there's no horizontal asymptotes to worry about today. Eventually, we'll get to that point. But the next couple examples are only going to have this situation where the degree of the numerator is larger. So 3 steps. First step, step 1, I want you to find the zeros. And remember, you find the zeros by setting the numerator equal to 0. All right, so set a of x equal to 0, then you'll be able to solve for x. That's step 1. That'll give you kind of like a starting point, I guess. Step 2, draw the asymptotes. So you've also got to find your vertical asymptote by setting b of x equal to 0. And then you check your rules for horizontal asymptote. Like I said today, there isn't going to be a horizontal asymptote, but it doesn't mean that we're never going to see some that don't have horizontal asymptotes. Okay, step 3, make a table and draw the graph. Okay, we're going to use a table in our calculator to kind of help us fill in the blanks because we'll know where the zeros are, we'll know where the asymptotes are, so we want to make sure we have a good representation of everything in between. All right, so that's our step-by-step process. We are going to return back to that as we look at these couple of examples here. So example 1, part A, we've got f of x equals x squared minus x minus 6. And then we have that over x plus 1. So we're going to start by finding the zeros. Okay, so step 1, find the zeros, set x squared minus x minus 6 equal to 0. Since this is a quadratic, we solve it by factoring. So we want to start with x and x. Looking at these two numbers, we want to know what multiplies to -6 and adds to -1. So first of all, if I'm multiplying to a negative, I know one of them is negative and one of them is positive. And then the fact that I add to a negative means my larger number will be the -1. So for 6, it's 3 times 2. The 3 is bigger, so I know I put it with the -1. So then we solve these, set x minus 3 equal to 0, and I get x equals 3. And then set x plus 2 equal to 0, and I get x equals negative 2. So those are my zeros. So I'm actually going to start plotting as we go here. Okay, so 1, 2, 3. There's 1. And then negative 1, negative 2. There's another one. Okay, so just to start, those are my x-intercepts, aka my zeros. Step 2, find the asymptotes. So vertical asymptote, we set the denominator equal to 0, and we get x equals negative 1. So at x equals negative 1, we're going to draw on our little dashed vertical asymptote that we did throughout the whole last section. Remember, that's a line that we'll get very, very close to, but will not actually touch or cross. And then for horizontal asymptotes, the degree is larger in the numerator, and so I don't have a horizontal asymptote. So no horizontal asymptote. So like I said, I am going to set up a little table, come up with some points, use my calculator to do that, and then I will be able to graph. So I'll do a horizontal table since I'm pretty much out of space. Let's pick some good values to plug in. Okay, so maybe let's plug in like 0, 1, and 2 just so we can see this picture over here. Then we should probably see some stuff over to the side here. So this is a negative 3 and this is a negative 4. So basically once you have the graph in front of you, that's going to help you determine what values you should plug into your table. There's no like preset number of values that you should be using. We'll just kind of eyeball it and see if we get a good graph. So open up a calculator page and then remember how to do that define thing. So hit menu, number 1 for actions, number 1 again for define, and then plug in this function right here. So f of x, you've got to put the x in parentheses, equals, and then since this is a rational function, do your little fraction key, hit control, and then divide, and you can open up a fraction. X squared minus x minus 6 is the numerator, and then x plus 1 is the denominator. So remember with this setting, it'll just say done, and then you can just plug some different things in. So f of 0 gives me negative 6. F of 1 gives me negative 3. F of 2 gives me negative 4/3, which is negative 1 1/3. Now we're going off to the other side, negative 3. So f of negative 3 is negative 3. And f of negative 4 is negative 14/3, aka negative 4 2/3. Okay, so let's see if this gives us a good enough picture. If it doesn't, we'll just plug in some more points. Okay, so 0 is down at negative 6. 1, 2, 3, 4, 5, 6. It's right there. 1 is at negative 3. 2 is at negative 1 1/3. And then we've got negative 3 is down here at negative 3. And then negative 4 is down at negative 4 2/3. It's right around there. Okay, so let's see if we can figure out what this thing is going to do. So we know that it's going to hug this vertical asymptote. Okay, so we know it's going to come down here. It's going to go through these points. Okay, so I know that much. Same thing here. I know it's going to hug this vertical asymptote, go like this. So we've got something like that so far. But then we know that there isn't a horizontal asymptote. So we know this isn't going to level off and this isn't going to level off, which means this must just keep decreasing and this must just keep increasing. Okay, so let's take a look at exactly what we've got. Okay, so if we look at some more points, you'll see, and this is, I just plugged the graph into the calculator just to show you. So you can see this just kind of keeps increasing like this, and this just kind of keeps decreasing like this. All right, so not the prettiest of graphs, but at least it's something. All right, let's look at this one. Same 3 steps. Step 1, we're going to find the zeros. I'm going to take the numerator, and I'm going to set it equal to 0. So I'll start by cube rooting both sides. That's the first algebra I need to do. When I cube root both sides, I get just the x plus 1 here, and the cube root of 0 is still just 0. So I end up with x equals -1. So I'm going to plot that, my one and only x-intercepts, right there. Step 2, I want my vertical asymptote, which I'm going to get by setting the denominator equal to 0. Okay, in this one, I square root both sides to try to get the x by itself. When I square root the left, I have just the x plus 2 left over, and the square root of 0 is still 0. So my vertical asymptote is an x equals -2. Okay, so that's where I'm at so far. Horizontal asymptote, this technically has a degree of 3. This has a degree of 2. So I know my numerator's degree is larger, which means there's no horizontal asymptote. So that leads me to step 3, where I'm going to set up a table, and then graph it. Okay, so we've got this point right here. Let's plug in 0 to see what that's doing, and then let's skip around a little bit. Let's not go back to back to back. Let's do like 0, and then 2, and then 4 to get a good idea on the right-hand side. And then this is -2. So let's do like -3, -5, see if that gives us a good enough picture. Okay, and I'm just kind of randomly selecting these values. Like I said, there's no pattern that I want you to follow exactly. So we're going to do menu and then 1 for actions again, 1 for define. Type in your function, f of x equals, make sure you type in a little fraction. Careful with this piece, make sure you put parentheses around the x plus 1 before you raise it to the 3rd power. And then again, make sure you have parentheses around the x plus 2 before you raise it to the 2nd power. So that's our function. I'm going to plug in first a 0. Whoops, got to do f of 0. And I get 0.25. And do f of 2. And I get this about 1.69. F of 4. Get 3.47. So these are all going to be estimates, obviously, that I'm drawing on there. F of -3 gives me -8. And then f of -5 gives me -7.11. Okay, so let's plot these values, like I said, see if it gives us a good enough picture. So 0, we are at 0.25, which is right about there. And then 1, 2, we're at 1.69, so maybe about there. 3, 4 puts us up at 3.47, so right about there. And let's go off to the other side. The other side, -3, I'm supposed to be down at -8. 1, 2, 3, 4, 5, 6, 7, and 8. And then at -5, so we're just going to take up this whole space here. -4, -5, I am at -7.11, so right around there. Okay, so we know we've got the vertical asymptote. Now this part's a little bit weird because this piece is just going to kind of come this way and then it'll go down like this, okay, down the vertical asymptote. So that means this one, when it comes this way, it actually ends up going up the vertical asymptote like that. Okay, so that one's a little weird because this one already went down the vertical asymptote, so this one goes up the vertical asymptote. The way you can check that for sure is by plugging in something right around there, like -1.5. Oh, and that one is at -0.5. I may have lied about that. All right, let's investigate this further. So -0.5 would be right around there. I'm sorry, maybe forget that ever happened. Let's plug in something even closer. How about f of -1.8? Oh yeah, oh that one shoots way down. Okay, so forget about that. Maybe this side goes way up. Sorry. Okay, now this side, let's plug in something even closer. So this is -3. Let's plug in something in the middle. F of -2.5. Okay, I guess that one shoots way down as well. So we'll see if I can maybe get, I don't know if I have whiteout or anything. Hopefully you guys are over it. So yeah, scratch that. So this kind of comes down here, curves around a little bit and goes this way. which is why it's very important to use a table to plug in a whole bunch of different values to determine. So I'm going to run my vertical asymptote down a little further. So a very strange looking graph. That's what these rational functions are. There's like no patterns in them at all. Okay, last function here. Kind of a story problem. Company uses this formula right here to determine the salary in thousands of dollars, and an employee during his Xth year. So if you wanted to know the first year, you'd plug in 1. If you wanted to know the 10th year, you'd plug in 10. What domain and range values are meaningful? So we'll talk about that, and we're going to set this graph up, all right? So we have, first of all, normally we would do like the zeros, and we do vertical asymptotes and stuff, which we're still going to do. So step 1, to find the zeros, we would set 45x plus 25 equal to 0. Do a little work here, so minus 25. Okay, so here's what this ends up solving for. We reduce this down and you get negative 5/9. So what this tells you, what I plugged in for 0 was the salary. So this is basically trying to figure out when your salary would be equal to 0. And what this tells you is that your salary would be equal to 0 when you have worked there for negative 5/9 of a year, which is exactly what they mean by what domain and range values are meaningful in the context. This means absolutely nothing in the context of salary. So it's very, very important that we're checking these things out. Number 2, if we're looking for a vertical asymptote. Vertical asymptote is something that your graph is not allowed to touch. And so we set x plus 1 equal to 0 to do that, and we get x equals negative 1. So at negative 1, that means you've worked there for negative 1 years. You don't work somewhere for negative 1 year. So that is not meaningful in the context of the problem either. So let's go back to this question. Domain. Domain only makes sense for values that are greater than 0. We're only talking about people that have worked there, not people that have never worked there, aka 0 years, not negative years, because that doesn't even make sense. And then same thing with range. Range, it only makes sense to talk about positive values of salary. They're not going to take money away from you. So it's really, really important to think of these problems in the terms of their context. Okay? Last thing is that we are looking at a horizontal asymptote. So for the first time, we get to use a different horizontal asymptote rule. If we look here, we've got a 45x and then an x. Those degrees are the same. They both have a degree of 1. So for the first time, we are going to be using that that last rule that says that you take the ratio. So horizontal ratio of 45 over 1. So 45x over 1x, which of course is just 45. All right, so what this means is that the horizontal asymptote is 45, so you're going to get closer and closer to 45 but never hit it. So it makes it sound like maybe that's their top salary rate that you're never actually going to hit. So it's like a salary cap, I guess, which is not a very high salary cap. But let's plot some things anyway, all right? So the first value of x you're allowed to plug in is 0. So if you were to plug in x equals 0, these two pieces would be 0 and you'd have 25. Okay, so let's go 5, 10, 15, 20, 25. So that's your first year salary. And then the horizontal asymptote is 45. So I'm killing it on space management here. Okay, so 30, 35, 40, 45. So for this one, just try to pretend these are two separate graphs because they're supposed to be. For this one, you've got a horizontal asymptote, okay? So what's going to happen with this is your salary is going to grow at kind of a curved rate until you get to 45, and it's like a salary cap. It kind of levels out. It's a horizontal asymptote. Okay, so the meaning of the horizontal asymptote is that it is a salary cap. That is the highest that they will ever pay you at that company, which means that maybe you should not join that company. All right, so we're going to take over in the next lesson with an 8.4 day 2.